So in this video we are going to briefly discuss functional groups. But first I'd like to show you one other really cool feature of bond line structures. Essentially what I'm going to show you is that with bond line structures, with the help of bond line structures, it becomes much easier to see chemical reactions occurring. So in general, it is hard to see what's going on for a chemical reaction with Lewis structures. So let's look at an example. We'll have, this is an alkene. It's drawn in a partially condensed structure, and so we're going to hydrogenate the alkene. So with H2, hydrogen, and platinum as the catalyst, and we're going to see this reaction in chapter 8, really. So you don't have to know this reaction for now. I just want to demonstrate to you how much easier it is to see a reaction like this with bond line structures. So anyway, the product of the reaction is a fully hydrogenated alkane, and you see it has changed a little bit, but you see the difference here. Essentially what happened is the double bond on the left has disappeared on the right, but it's kind of hard to see what's going on. Now if we show the same reaction in line draw format, you immediately see that this double bond gets hydrogenated. Yeah, and so essentially bond line structures make it much easier to see functional group transformation. So functional group transformation means we have a group of atoms, for example a double bond, which gets removed in the product, or gets changed in the product. So in general, we want to now look at specific functional groups. There's a couple of them you really need to memorize. And why do you need to memorize it? Because these characteristic groups, these functional groups, this is again specific arrangements of atoms, they always react in a similar manner. So it's really helpful to know functional groups to predict reactivity. That's why you kind of have to learn them. And you will see that the book, your textbook, is actually structured in a way where it starts to discuss the reactivity of different functional groups. And yeah, so what do you need to know? We're going to make a table. We're going to, on the left column, we're going to put the functional group, middle, the name of the functional group or the classification, and on the right, we're going to have an example for all of these. So, I'm going to start with a simple functional group. It's called it's an RX, where X is just a halide. So either chlorine, bromine, or iodine. And this functional group, first of all, the R always means it's the remainder of the molecule. So whatever else is attached, which is not part of the functional group, right? So this functional group, the RX, is called an alkyl halide. And an example would be 1-chloropropane. Again, a propane is a carbon chain with 3 carbons, and we'll learn that in chapter 3, the naming. So don't worry about the naming as of yet. Now we will just continue this table, and you pretty much have to memorize it for now. But this will become second nature to you once we've started discussing the reactivity of all of these functional groups. So the next one we want to look at is a functional group called an alkene. It's basically a carbon-carbon double bond, and then just other groups attached. So the R's, they can be either hydrogen, or they can be methyl or ethyl or anything else. They don't have to be all the same as in this molecule. They can be, R can be one thing on one side, and then you can have R1, R2, R3, and R4. So in this, an example would be 1-butene. Now this we're talking about a carbon chain with 4 atoms, so we call it a butene. A carbon-carbon triple bond, on the other hand, is called an alkyne. So notice the difference there, right? Carbon-carbon double bond, an alkene, E-N-E at the end, and an alkyne, Y-N-E at the end for the triple bond. And again, an example would be 1-butyne. Right? So all we're changing there is from butene to butyne. We are making the double bond into triple bond. Another common functional group, for example in sugars, which is there a lot in biology, is called an alcohol. Okay, so you know ethanol, of course, that's the alcohol people sometimes drink and get drunk with. But in general, and that's an ethyl group with an OH group. But now here we are looking at alcohols in general. and it's just an OH group is an alcohol. Again, we have an example here that would be 1-butanol. Then we can take the OH group and replace the H with an R, right? So something like methyl or ethyl, and then we have an ether functional group. And the diethyl ether, which you will lose in the laboratories, is a common example, common solvent. So we're going to look at some more functional groups. We just looked at the alcohol, which is an OH group, and the ether, which is an oxygen like kind of attached to two R groups. And now you can have the exact same thing with sulfur. And in this case, so the RSH version is called a thiol. An example would be 1-butane thiol. And why are thiols important? Because they're again present in many biological compounds, but in general they're extremely smelly. Okay? Extremely smelly. Smells like fart, kind of, these thiols. So really, really strong smell. And then you can have the version of an ether with a sulfur that's called a sulfide. And here again we will have an example. And then, we move on. Okay, so now we looked at double bonds. But now if you have special arrangement of double bonds, basically 6 atoms in a ring with 3 double bonds, it's an especially stable structure. It's called an aromatic ring or an arene ring. And example here would be methylbenzene, or it's also called toluene, which I think you will use in the laboratory as well. Common solvent. Okay, now we can have oxygen, other oxygen-containing functional groups, and the one I'm drawing here is a ketone. So you have a double bond to an oxygen and then 2 R groups. That's important. 2 R groups, so 2 methyl groups or 2 ethyl groups or 1 methyl and 1 ethyl. They have to be R groups. They can't be hydrogen, because then it's a different functional group. Then it's an aldehyde, as we'll see. Example here would be 2-butanone. And I forgot to draw you to tell you the name of this sulfide example. That's a diethyl sulfide. Okay, so a few more functional groups. Then we're done. Let's just continue the table. I think that's going to be the end of the table on both of these 2 pages. So we're going to learn about, I think, 5 or 6 more examples, or 8 more. Okay, so we just saw the ketone, which has 2 R groups attached to a carbon with a carbon-oxygen double bond. Now, if you replace one of the R groups with hydrogen, then it's called an aldehyde, right? So that's an important distinction, okay, because the reactivity is fairly different. And so an example here would be butanol. And now this hydrogen, which we placed there in the aldehyde case, we can replace it with an OH group. Right? And in this case, we get a carboxylic acid. See, so these functional groups are all related. We're just changing out part of those groups. And an example here would be pentanoic acid. Another example we have already seen in lecture would be acetic acid, right, which is in vinegar, which has just two carbon chain, an ethyl chain. Now again, you can take the OH group and, for example, put an X there. So X again would be chlorine, bromine, or iodine. Then it's called an acyl halide, and example would be acetyl chloride. Right, and then one more. So you can actually take 2 carboxylic acids, put them together, and take one OH group away, and link them together at the central oxygen. Then it's called an anhydride. Again, similar structures, but they all have different names. They have different reactivity. I have to learn about it. And this acidic anhydride. Why? Because it's basically 2 acidic acid molecules condensed together. We're going to finish up the table. Now, of course, instead of putting another acid group next to an acid group, like in the anhydride, you can just, instead of having OH on the carboxylic acid, you can replace that H with an R group again, right? And then it's called an ester. An ester. And ethyl acetate is a very common example, solvent you will use in the laboratory. Finally, look, we had an OH group and an OR group. You can replace that with an NR2 group. And then it's called an amide. And why do we care about amides? Because it's the bonds which hold together proteins. Very, very, very important for biology. Okay? And so here's an example. This would be butane amide. The last functional group you need to learn is an amine, or amine in British English. So an amine, it's just a nitrogen with 3 R groups. So R can be either hydrogen or again an alkyl chain like methyl, ethyl, propyl, hexyl, etc. Right? And sorry, an example here would be diethylamine. So you need to learn these. These ones you need to memorize, and I will ask questions on an exam. So usually what I will ask is I will give you a molecule. In this case, I'm drawing atenolol, which is a common medication. I could draw another example. So we have 2. This would be enalapril, which is also another biologically useful molecule or medically useful molecule. And so we're going to look at functional groups. We're going to start on the left, and I've already highlighted this NH functional group. So what is this? This is an amine. Next to it we have an alcohol, then we have an ether, and then we have an aromatic ring, and finally we have an amide. Okay, so it's not too hard to assign these functional groups. You just have to recognize the pattern. What is very important though is to note the following. So look, we have a double bond here inside of the aromatic ring, but it's not called an alkene. Because why? Because the double bond is part of a much larger pattern which matches as an aromatic ring. So it behaves very differently than an alkene. So another example here would be, you have an NH2 group with something attached, but because it's attached, it matches the amide functional group pattern, the larger amide group pattern. It's not an amine. It's actually an amide. You see, so you always want to match the largest possible pattern. That's very important. Now, we can finish up the example on the right. So here we have a carboxylic acid. We have another amide. We have an amine, that's right. And an ester. And finally, an aromatic ring. Okay? So that's all I want you to know about functional groups. I would recommend you make some flashcards and then, practice these, learn them. And we will keep practicing them in lecture and also do some book problems to practice them. Okay? Thank you very much for watching.